Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to solve some of the problems on simple harmonic motion. Now, let us give a brief descriptions about simple harmonic motion. For this simple harmonic motion here, a body is said to be under a move or vibrate with a simple harmonic motion. It has to satisfy the following two conditions. The condition number one is that the acceleration is always directed towards the center, and that is known as the center, that is known as the mean position or reference line or the point of reference. And the second one is that its acceleration is proportional to the distance from that point. That means here the acceleration is always directed towards the center. In order to explain simple harmonic motion, the best things are, there are two things. Through them we can explain it. One is spring mass system, another one is simple pendulum. So by considering the spring mass system, the spring and it is the mass, the spring is having a stiffness of K. It is the equilibrium position or mean position. With this equilibrium, when you give initial displacement x, it starts oscillating with respect to equilibrium position. That is, this is another and this okay. If the mass moves from this position to this position or here to here, it will move. It starts oscillating, vibrates. Now here the acceleration, this x is the displacement, and what about velocity component? X dot is dx by dt, and acceleration component is x double dot equal to d square x by dt square. This acceleration is always directed towards the center known as this acceleration. Even though you may have to have given displacement in positive x direction downwards, but the acceleration, that is the initial acceleration, is always direct towards the mean position. Okay, that is the first condition. And the second condition is that its acceleration is proportional to the distance from that point. The point from here to is proportional to the distance, that is the acceleration is proportional to. Now, the elastic force which acts to come back to the mean position, that F equal to minus K times X. The stiffness force or elastic force or restoring force is directly proportional to the X. That is the displacement. This F is, what is the F equal to mass times acceleration, that equal to minus K times X. The what X double dot equal to minus K by M times X. This acceleration is always directed, is proportional to the displacement. X is acceleration, X double dot is proportional to X, and is always directed towards the mean position or reference point or reference position. So these are the two conditions should be satisfied. When the system is satisfied these two conditions, then the system is under simple harmonic motion. Now that is for linear. Now by considering the angular simple harmonic motion, to explain it, what is the displacement, what is the velocity, and what is the acceleration of the particle P. Here the particle P is moving in circular direction. That's why it is the particle P is under angular simple harmonic motion. Angular simple harmonic motion. Now we are considering the particle here. We are going to explain it, the velocity and acceleration of a particle moving in angular direction and having a simple harmonic motion SHM. Then how to calculate, how to derive the expressions, the velocity and acceleration of the particle P. Now we are considering the particle, it is moving in circular along the circumference of a circle, and which is having a radius r with a uniform angular velocity omega radians per second. Okay, it is shown figure here. The theta equal to angular displacement, theta equal to omega times t, where t is the time, omega is the angular velocity of the particle, that is uniform angular velocity, that is theta equal to omega t. Now When the P is moving in circle around the circumference of a circle, the projection of the P on axis OY dash is up and down. It is in up and down motion. That's why the motion of the projection of the particle P on the axis y dash is in simple harmonic motion. Now, what is that R radius? Here, the radius of that particle from the center O. This radius is known as the maximum amplitude when P is at y. Now, let us discuss furthermore. Let P is the particle position at which the angular displacement at that instant of time t from x. Therefore, the angle turned by the particle at the time t and theta equal to omega times t. That is in radians, where omega is the angular velocity and t is the time and theta is the angular displacement. Now, from this triangle OPN, and here the displacement is the displacement of the point, that n is n, that is the projection of the point P on axis OY, that is vertical y dash circle of the circle. This how it comes here. This making an angle, this ON is the right angle triangle. This angle is nothing but equal to this angle. That's why here that ON equal to OP sin theta, or y equal to, what is the distance? That is the distance of y equal to ON, that ON equal to whatever here, that OP is nothing but R sin theta. Substitute in the place of by plugging the value of theta in this relation, that is R sin theta. Then what will happen here? R sin times theta is nothing but omega t. That's why y equal to R sin omega t. That is the equation. This equation is the displacement equation. That is y equal to R sin omega t. The displacement equation, differentiate displacement equation with respect to time, the velocity will be obtained, and differentiating the velocity equation with respect to time, then acceleration can be obtained. Now let us see further. Now differentiating that equation, that dy by dt, then velocity, that is r omega times cos omega t. Now here the velocity v dy by dt is nothing but a velocity. That velocity v equal to r omega. What is cos omega t? Sin square omega t plus cos square omega t equal to 1. From the trigonometric relations, now sin square omega t equal to 1 minus cos square omega t. Now what about single term sin omega t equal to under square root of 1 minus cos square omega t. Substitute here that in the place of cos omega t, cos omega t, then it becomes 1 minus under square root of 1 minus sin square omega t. From this relation, we can substitute in the place of cos omega t as under square root of 1 minus sin square omega t. That is a velocity equation in terms of uniform angular velocity and where r is the amplitude. Now from the equation 1, what is sin omega t equal to y by r, where y equal to r times sin omega t, then sin omega t equal to y by r. Substitute here in the place of sin omega t again y by r, then it becomes y square by r square. And here what will happen here, v equal to r omega times under square root of 1 minus y square by r square. Then further simplification, r omega times r square minus y square by r. Okay, here r get cancelled. Then finally the velocity v equal to omega times under square root of r square minus y square. This is the velocity equation, that is in terms of uniform angular velocity, and r is the amplitude and y is the displacement, that is on. Yes, this is what obtained here, the velocity, that v equal to omega times under square root of r square minus y square. Now we want acceleration component. What to do? Derive again. Take it this dy by dt with respect to time. If you differentiate it, then we'll get it, the acceleration relation. Now d square by dt square equal to minus negative of r omega square sin omega t. Now for acceleration, that is nothing but here a equal to minus omega square y. Y comes here, r times, if you simplify it, minus omega square times r sine omega t. This r sine omega t is nothing but a y. Then substitute here minus omega square y. Now this is the equation of simple harmonic motion acceleration. That is where omega is the uniform angular velocity and y is the displacement and a is the acceleration. So a is proportional to y. Displacement acceleration is directly proportional to the displacement. But then acceleration equal to minus omega square y. This omega square is the constant of proportionality for simple harmonic motion. Alright. Now this equation we can compare with the equation of motion of a spring mass system. Then the circular frequency can be obtained. How to get it here? Let us see. If we consider a simple the spring mass system, the equation of this is m and it is k. So draw the free body diagram. This is the kx, and here the mass times acceleration m into x double dot. Now the inertial equation, it acts in opposite direction. Inertia m into x double dot plus kx equal to 0 by using the D'Alembert's principle, okay, or Newton's second law of motion. Then m into x double dot, then m into x double dot equal to minus k times x. Further simplification, x double dot equal to minus k by m into x. Now here the comparison is that x double dot equal to minus k by times x, and where acceleration equal to minus omega square y. This is also amplitude, this is also amplitude, yeah, this is also displacement, x also displacement. X double dot is the acceleration, where a is also acceleration. If you compare, the similarity is that omega square equal to k by m. From that, omega equal to under square root of k by m. This is the circular frequency. Okay, that is a derived expression of a circular frequency. Now here, what is the significance of the negative sign in this acceleration expression? That is a equal to minus omega square, negative omega square times y. So this minus sign indicates, negative sign indicates that the direction of the acceleration is always opposite to the direction of the displacement, in which y increases. If y is increasing, acceleration decreases. Okay. So the direction of the acceleration is opposite to the direction of the direction of the displacement. So that's why here, what is the meaning of here? The acceleration is always directed towards the reference point or mean position. But here, okay, that's the meaning, significance of negative omega square times y. Now let us come to solve the problems based on those derived expressions. Let us begin. The position of a steam engine moves with SHM, simple harmonic motion. The crank rotates at 120 rpm, revolutions per minute. This is the data. And the stroke length is 2 meters. Find the velocity and acceleration of the piston. There are two objectives are to be calculated when it is at a distance of 0.7 meter from the center. So it is 0.75 meter from the center. The stroke length was given here, that is 2 meters stroke length. That is nothing but the amplitude, that is capital R, small r equal to 2 meters. And the distance from the center, that is 0.75 meters. And the frequency of the piston was mentioned here, that is 120 revolutions per minute. So omega equal to 2 pi n by 60. Now we have to find out the velocity equation. Now velocity of the piston, first objective is that velocity, angular velocity of the piston, that is omega equal to 2 pi n by 60. And 2 pi times, what is the n equal to 120 by 60, then obtained value is 4 pi radians per second. Now coming to velocity of the piston, we know the relation, expression is that v equal to omega times under square root of r square minus y. R square minus y square. This omega is obtained values of 4 pi radians per second, where r is 1 meter, y is 0.7 meters. Substitute here in this derived expression, the obtained value is the velocity of the piston is 8.3 meter per second. Alright. The next objective is acceleration of the piston. Directly substitute, that is a equal to negative square times omega square times y. Here, what is the omega equal to 4 pi radians? Substitute here, y is the 0.75 meters. After getting substitution, the calculated value is 118.4 meter per square second. Okay, these are the simple there are two objectives: velocity of the piston and axle of the piston for the given data of revolutions n, r, and y. Now coming to next problem here, a body moving with, again we are going to discuss only simple harmonic motion. A body is moving with simple harmonic motion, has an amplitude of 1 meter directly given, that is r equal to 1 meter, and the period of complete oscillation is 2 seconds, that is time period t, 2 seconds. The next one is that what will be the velocity and acceleration of the body after 0.4 seconds from the extreme position? What will be the velocity v and acceleration a of the body after 0.4 seconds from the extreme position? Now, okay, the time taken, the period time is 2 seconds, but the time taken by the body from the extreme position, that is 0.4 seconds. Okay, let us begin. Okay, the body is here. What is here? It is under amplitude of complete oscillation. It is not mentioned when the body is in linear or angular motion. So, we are considering it as the amplitude of 1 meter and period of, yes, the amplitude of, we discussed or derived expressions from the angular simple harmonic motion. That's why we assume that the body is under, the particle is moving in circular motion along the circumference of a circle. Now, here O be the center, Y, capital Y is an extremity of the motion, and P is the position of the particle of the body or body after 0.4 seconds from Y axis. Okay. Now, how to make it? The time required by the body to travel from Y to P. Where is the Y? Y to P is how much? 0.4 seconds. Now, time required by the body from 0 to Y, how much it will take it? That is 1/4 of the total time period. That is T by 4. 2/4, that equal to 0.5 seconds. Okay, 0.5 seconds. After that, time required by the body to travel from O to N, from here to here. How to get it from here to here? That is O to Y minus Y to P, Yn. That's why here 0.5 minus 0.4, that is 0.1 second. Now, angular velocity of the body omega equal to 2 pi by t. Okay, that is 2 pi by time period, that is 2 pi by 2, that is pi radians per second. Now, we know omega and we need displacement y equal to r times sine omega t or cos omega t. Now, here displacement of the body is 0.4 after 0.4 seconds from the extreme position, that is r 0.1 seconds from the mean position. Okay, then y equal to r times cos omega t, r equal to 1 meter, cos times omega equal to pi radians per second, and where is the t is 0.1 second. Then it becomes 1 times cos 18 degrees. So that is 1 times cos, that is pi times 0.1. That is here pi times 0.1 is how much? How to get it? 18 degrees. Cos 18, that is 180 times 0.1, that is 18 degrees. Then if you substitution and calculating the value of 1 times cos 18 degrees, that is 0.95 meters. The next term is that objective is velocity of the body. The velocity of the body v equal to omega times r square minus y square. Here, by plugging those values of omega, r and y, the r value is 1 meter, y value is 0.95. Just now we calculated here 0.95 meters, that is y equal to 0.95 meters, and r equal to amplitude, that is 1 meter, that is omega is the pi radians per second, pi times under square root of 1 square minus y value, that is 0.95 whole square, that is the obtained value is 0.98 meter per second, that is the velocity of the body. Then if you know the velocity of the body, the acceleration of the body, that is a equal to omega square times y. The a equal to omega square times y, what is the omega? The omega is the pi radians, pi, that is then pi square, then 0 times 0.95, that is 9.38 meters per square second. Acceleration of the body and the velocity of the body. These are the two objectives are calculated here. The next problem we are going to solve it is related to the simple harmonic motion. The objectives are the amplitude and time period of a particle. That is the problem here. So find the amplitude and the time period of a particle moving with simple harmonic motion, SHM. which has a velocity of 9 meters per second and 4 meters per second, as velocities of, yes, at a distance of 2 meters and 3 meters respectively from the center. Here the objective, here the data was given, here it is, the velocities v1 and v2 and the displacements y1 and y2, v1, v2 and y1, y2. There are two equations and two unknowns can be calculated, that is amplitude and time period. That is, let us begin. Amplitude of the particle, where r is the amplitude of the particle and omega is the angular velocity. Then velocity of the particle, we know the equation, that is v equal to omega times under square root of r square minus y square. Now v is the 9. Here amplitude was not given to be calculated and y was given here. At 2 displacement, the velocity is 9 meters, that is 9 meters per second. 9 equal to omega times under square root of r square minus 2 square. Then 9 equal to omega times r square minus 4. That is one equation. The second equation, that is v2, that is 4 equal to omega times r square minus y 3 square. That is omega times r square minus 9. Now 9 by 4 equal to this equation by this equation, or if you square it, 9 square equal to omega square times r square minus 4. 4 square equal to omega square times r square minus 9. Or substitute equation 1 by equation 2, then omega will be cancelled at numerator and denominator. Then 9 by 4, then if you square it on both sides, both LHS and RHS, then 81 by 16 equal to r square minus 4 by r square minus 9. Make it cross multiplication, 81 times r square minus 9. 81 times r square minus 9 equal to 16 times r square minus 4. 16 times r square minus 4. Then 81 r square minus 81 times 9. 9 ones 9, 9, 18, 72, 729. That equal to 16 r square minus 16 into 4, 64. Now 65 r square equal to, the 16 goes, that's 729. Okay. So then 65 r square equal to 729 minus 64, that is 665. Then r square, r equal to 3.2 meters. That where r is the amplitude. Okay. Now whatever the time period of the particle. Now we are going to substitute what is the time period. If you know the omega, then time period t equal to 2 pi by omega. Now substitute any one of the equation, that is equation 1. Substitute the value of the r in equation 1. 9 equal to omega times r square minus, that is r is 3.2 whole square minus 4. What is the equation here? 9 equal to omega times r square minus y square, that is the 2 square. That is 9 equal to omega times r square minus 4 is the equation. Now substitute here r equal to 3.2 whole square minus 4. Yes, 3.2 whole square minus 4. Then it will happen, it is not a imaginary value, but the real value is obtained, that is omega times 2.5 equal to 9. And omega equal to 9 by 2.5, that is 3.6 radians per second. We know the angular velocity, uniform angular velocity of the particle, then time period t equal to 2 pi by omega. Then substitute here 2 pi by 3.6. The obtained value is 1.75 seconds. Here it is that is the 1.75 seconds. Okay. This is there are two objectives are to be calculated here. One is amplitude. The obtained amplitude is 3.2 meters and the time period of the particle, that is 1.75 seconds. Okay. The next problem here it is, in a system, the amplitude of the motion is 5 meters and the time is 4 seconds. Find the time required by the particle in passing between points which are at a distance of 4 meters and 2 meters from the center of force and are on the same side of it. Okay. In a system, again, the amplitude of the motion is 5 meters. Amplitude of the motion, that is r value is 5 meters and the time taken is 4 seconds. And distances which are at a distance of y1 and y2, the distance at 4 meters and 2 meters. Okay, that's an area of the same side of it. Yes, the center of force and are on the same side. Now, we are considering angular simple harmonic motion. Based on the data, Here it is at a distance of 4 meters and 2 meters on one side, on the same side. Okay, the maximum amplitude R, that is 5 meters. Y1, Y2 and time taken 4 seconds and 4 meters, 2 meters. And what to be found, the time required by the particle in passing between points, between these 2 points, what is the time required? So for that, angular velocity of the particle omega equal to 2 pi by t, 2 pi by 4, that is 90 degrees. Okay, that is pi by 2, 90 degrees, or pi by 2 radians per second. And displacement of the particle y equal to, that is y equal to r times sin omega t, y equal to 4, that is y1 and y2. We know the two equation, that is y equal to r times sin omega t or cos omega t. Okay, now here substitute here y1 and r1. We'll get the equation that 4 times 4 equal to 5 times sin omega t1. Sin omega t1 equal to 4 by 5. From that, omega t1 equal to 53.1 degrees by t1 equal to 53.1 by 90 degrees, that is 0.59 seconds. Both are in degrees, or if they are both are in radians, you have to make it. Here already it is in degrees. That's why here degrees by degrees for maintaining the dimensional homogeneity. That is t1 equal to, after maintaining it, t1 equal to 0.59 seconds. Now similarly, the second equation, y equal to omega times sin omega t2, that is 2 equal to r times sin omega t2. Sin omega t2, where is, what is the r is 5, that's 2 by 5 equal to 0.5. From that, t2 equal to 0.26 seconds. Then we need, there are two things. One is t1 at a distance of 4 meters, 0.59 seconds. And t2, what is the t2 here? The t2 is 0.26 seconds. It is at a distance of what? 2 meters. So t1 minus t2, that is the distance between 4 meters and 2 meters. That's why t equal to the time required in passing between the 2 points, that is t equal to t1 minus t2, that is 0.59 minus 0.26, that is 0.33 seconds. Okay. We can also solve some of the problems based on the equation of motion, such as spring mass system. The spring mass system is under the vibration of longitudinal vibrations. So for this, the circular motion is omega x, that is x value here equal to, there is omega n equal to square root of k by m. Now, what is the natural linear frequency or natural frequency? That is omega n by 2 pi. That is 1 by 2 pi times under square root of k by m. Okay. So here, based on the data, the formulas are to be used. What is the time period? T equal to 2 pi by omega n. From that, type 2 pi by under root of k by m. Oh, this is also time period equation. Now, what is the equation of motion for the system? For this, mx plus mx double dot plus kx equal to 0. So this is m into d square x by dt square plus k times x equal to 0. This is the second order differential equation. Now d square x by dt square plus k by m into x equal to 0. So from this term is the omega n circular frequency under, and that's for angular simple harmonic motion, the frequency is under square root of k by m. So based on the data, we have to use the circular frequency calculations. So in this session, we calculated only the velocity and accelerations of a simple harmonic motion, provided the motion of the body is circular. That means angular simple harmonic motion consideration. Under that, we calculated the velocity, acceleration, amplitude, and also time period are calculated here. Now these are the references or used for this session. There is Arist Kurmi, Irving Shames, Hebler, and Bjorn Johnston for vector mechanics and also for engineering mechanics. So we can wind up the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.